I want you to meet Sally. Sally is a lead engineer at Mander Diffling, a leading provider of paper and other stationery products. She's been there from the very beginning, one of the first engineers they hired. Because of this, she knows the codebase inside and out, and she's extremely familiar with the issues of running the app in production. And Sally is sad today, again. And she's sad today because their queues are sad today, again. So she deals with the problem, makes the system happy, again, then goes back to her normal work. She's still thinking about this, though. This has been a problem for years, and no matter what they've tried, they never seem to be able to fix it. The next morning, after a good night's sleep, Sally wakes up with a solution, a radical new idea that will fix this problem once and for all. But to understand how this will fix all the problems, we're going to need a little bit of history first, and to understand how Mander Diffling got here in the first place. First of all, though, hi, my name is Daniel, and I work at Indeed Flex. We are a flexible staffing platform here in London. As you probably noticed, though, I'm not originally from here. I come from Argentina, so in case you were wondering, that's the accent. And now let's go back to our little paper company. When Sally joined Mander Diffling, there were only a tiny team of 3 developers, and they wrote the app that was running the entire company, buying paper, keeping track of the inventory, selling it, delivering it, etc. And at first, everything was running in just the one little web server, and that was fine for a while, but they started having some problem at some point, and so Sally decided to add a background job system so they can defer some tasks to the background and not have to wait until they're finished. And then there was a queue. And the queue was good. It solved a lot of problems for the team, so they started adding more and more jobs to the queue. And then the queue was still good, so more and more jobs got added to it. Our story begins. A few months later, Joey receives a support ticket. Users are reporting the reset password functionality is broken. Joey takes the ticket, works on my machine, he says, and he closes it as can't reproduce. Now, of course, the ticket comes back with more details, and the users are saying they're still not receiving the reset password email. And sure enough, when Joey tests this again in production, he indeed does not get the email. After a bit of investigation, turns out that the queue has 40,000 jobs in it, and emails are getting stuck there and going out late. Joey spins up some extra workers to get the queues to drain faster and marks the ticket as resolved, but this had customer impact, so he decides to call it an incident, and while he's writing the postmortem, he starts thinking, how can we prevent this from happening again? Now, Joey knows that when a job gets stuck in a queue is because generally other types of jobs are getting in its way, and one way to try and fix that is to try and isolate these loads so that they don't interfere with each other. You can't have all the jobs in one big bag and just pick out of them in order, right? Some of them are more important than others. Now, in some queuing system, you can set priorities for your jobs, and this lets some jobs skip the queue, if you will, and run a bit quicker. So Joey thought maybe that would be a good idea, but it turns out their queues don't support priorities. Jobs are picked up in the same order that they're put in the queue. As an aside, by the way, that's a good thing. Priorities are not going to actually solve the problem, and we'll see why later. Instead of priorities, though, in the system, what you need to do to isolate your workloads is to create separate queues. So Joey creates the high priority queue for important jobs, and because programmers love some symmetry, he also creates the low queue for less important stuff. A few days later, he actually finds some jobs that need to happen every now and then, but they're not urgent and they take a little bit long to run. Be a shame if something important was late because of them, so he puts them in the low queue. A few months down the road, and Joey is dealing with another incident related to queues. Turns out everyone's jobs are important, so the high queue now has lots of different jobs, and now critical transactions are not being processed fast enough because of some new job that's taking too long, and we're losing sales. And after another postmortem, Joey christens the critical queue. And he makes it very clear to everyone. I know your jobs are important, but only very critical things can go here. We cannot let this happen again. Guessing none of you are surprised. A few months later, the critical company has an outage, and critical jobs which are critical and normally finish in about a second were taking a whole minute to time out. This started backing up the queue, and 2 FA text messages, which are also critical, started going out late. Again. But by this point, the company had hired a very senior engineer from a much bigger company, and she brought a lot of hard-won experience with her. This is Marianne, and when she noticed the incident, she recognized the problem immediately and got involved. Marianne had seen this exact same pattern happen before, and she knows what the problem is. Organizing your queues based on priority or importance is doomed to fail. First of all, there's no really clear meaning of what is high priority or low priority, and yes, there are documents or examples of what should go where, but you can never predict everything that you're going to have to throw at our queues. Some of those jobs will also be very high volume or long running, and it's really hard to predict how all of these will interact with each other. But she's seen this before, and she has the answer. We have to have separate different queues for different purposes, no priorities. That way, jobs that run together all look similar, making performance more predictable, and it's also going to be much clearer what goes where. That way, if credit card transactions start having trouble, for example, they don't interfere with unrelated stuff like 2FA. Now, of course, you can't have a separate different queue for every single type of job, although some companies have tried, but you can define some for your most common things. Marianne sets up one for mailers, which are generally pretty important. She also notices we send millions of customer satisfaction survey emails, and those are not important, so she puts in a survey queue so they don't get in the way. A few months later, you have something like this, and jobs are humming along just fine. Every now and then, a new queue is born, and everybody's happy with this. For a while, fast forward a few years, and our little company has grown quite a bit by now. We have now a couple dozen developers, and as usual, they're separated into different teams, in this case, based on the different functionalities of the app. You have the purchasing folks buying the paper, the inventory people keeping track of it, the logistics team, etc. One day, the logistics team is having a little retro, and the math column is pretty long. The purchasing folks have done it again. It's the fourth time this happens this quarter. How many times do we need to tell them? That's how purchasing had this genius idea. Instead of calling vendors and asking for better prices, they could just auto-email everyone and let ChatGPT do the haggling. The feature was good, but a little aggressive, and there were a lot of emails, so the trucking company didn't get the notifications they needed, and shipments went out late that day. Again, it's not always purchasing though. We had trouble with sales doing the same thing too. And to be fair, we've also done this. Remember the ship apocalypse last Cyber Monday where we clocked every queue in the system and ruined everybody's day? The conclusion seems clear. We have all of these queues, but we have no control over what other teams are putting in them. And they don't know what our jobs are and what our requirements are for those jobs. There's only one way to fix this. Teams need to be able to act independently of each other. That's the point of teams. And just like that, the logistics team queue is born. And look, at least I didn't go for microservices, okay? Now, of course, it's not just the logistics team that gets this queue. They obviously share this idea with the other teams and ask them to do the same. And guess what? Not everything the logistics team does has the same urgency. So 3 months later, you end up with logistics high and purchasing low. And of course, usually high and low and mailers are still there because we have hundreds of different jobs in there and nobody knows where they go or what they do. This is starting to get hairy. And also, it's a good thing that we have VC money behind this company. But even then, at some point, somebody does notice that we're spending way too much money in servers, and they start asking questions. That's how we have 60 queues now, which basically means 60 servers. Most of those servers are not doing anything most of the time, but somebody has to set those queues. So an obvious decision is made. We can configure processes to run several queues at once, so we will group some of them together and reduce the server count. And guess what? Now, you may be asking yourself why I'm telling you this clearly facetious story about people making bad decisions, but the truth is, this isn't fiction at all. I've seen this exact same pattern develop in exactly the same way in pretty much every company that I worked in. Hell, I was a bunch of these developers with bad ideas, right? And I've seen this enough that I think this is a common progression that a lot of companies go through. You may have seen this too, and hopefully this talk will help you with some of these issues. Or if you haven't gone down this path yet, hopefully it can prevent you some headaches. The reason I think this is a common progression, by the way, is not that these characters are bad engineers. The thing is, when you're faced with these challenges, these steps do seem like the obvious solution. They make sense, and they solve the immediate problem. But the issue is that queues have interactions or behavior that are very hard to reason about. So when we propose one of these changes to fix the problem, it's really hard to predict what's the next problem that they're going to cause. So how do we get out of this? We first need to think about what actual problem we're trying to solve when we start making new queues. Because the problem is deceptive, and we tend to attack the wrong issue. The problem isn't queues, and it's not jobs or priorities or threads. The problem is the language that we use to talk about this. It often is. If you think about it, when you have jobs running in the background all the time, and no one notices. If someone notices, that's when you have a problem. But what is it that people notice? A job didn't run. Which generally actually means it didn't run yet, but I feel like it should have by now. Or put another way, a job is running late. And that's what the problem starts, right? Because what does late mean here? Many jobs don't get to start immediately once they get in the queue. This just happens all the time. They tend to wait a bit, and no one notices. Some may wait for entire minutes, and no one notices. Some others is really obvious, even if they're a tiny bit late. For example, you probably know this one. You have this app, you send a message to your friend, and it tells you when it has reached their phone. That took a second, and you didn't even notice. But if you think about this other scenario, you have this app, and it send a message to your friend, and it tells you when it reaches. How anxious are you getting right now? Is he in a tunnel? Did his phone run out of battery? Should I be worried? Oh, okay. Thank God he's okay. Now that job was late. So here's the issue, right? There's an expectation you have for your jobs that of how long it will be until they run. But that expectation is implicit. It's one of those I'll know when I'll see it kind of things where you know if it's running late. But if I ask you when you think that threshold is, you probably can't tell me. You got the database maintenance queue, right? Where you run a vacuum analyze every night on every table because there was a problem with statistics once 2 years ago and we'll never trust the database again. And that's running 20 minutes behind. Is that a problem? Certainly not. But what if the critical queue is running 20 minutes behind? Definitely a problem. But what if it's 2 minutes behind? Is that okay? What if the low priority queue is 20 minutes behind? Is that bad? The problem is the language that we use to define these queues and the jobs we put in them. We give them these fake names and it gets us in trouble. Because high priority, low priority gives you some relative idea. This is more important or urgent than that. But it gives you no insight as to whether your queues are healthy at any given moment and until somebody basically is missing some job and they start shouting. And as an engineer, it gives you no idea where you should put things. So what do you do when you're writing a new job? You look around the queues for something similar and follow that? You just guess just how important this job feels? The problem is the words we use. High and low priority doesn't give you anything useful. But the good thing is that the answer is also in this language, because this is what we care about. What we care about is not priority or importance or the type of jobs or which team owns them. What we care about is that a job is running late. The one thing we care about is latency. And that's how we should structure our queues. We should assign queues looking only at how much latency they can tolerate before it feels like they're late. And that is the problem our friends are having, right? They're trying to isolate their workloads, but their queues are not designed around the one thing that we care about. Remember, the symptom is always this thing didn't happen as quickly as it needed to. The one thing we care about with queues is latency. And that sounds simplistic, but I'm dying on this hill. Latency is the only thing that you really care about for your queues. Everything else is gravy. Now, there are other things you're going to care about in order to achieve that latency, right? Throughput, thread counts, hardware resources. But those are a means to an end. You don't really care about your throughput. What you care about is that you put a job in a queue and it gets done soon enough. Throughput is just how you cope with the volume to make sure that happens. So separating your queues based on purpose or per team, there's just roundabout ways to try and get that latency under control. But the issue is they don't center on that latency. They're roundabout ways. And what you want to do is attack the problem directly. Now, to be fair, the first approach was doing roughly the right thing. The high and low queues were trying to specify the latency tolerance for these jobs. The problem is that while that decision comes from the right instinct, high and low and super really extra high is extremely ambiguous. For two reasons, right? First, have this new job and it's just rolling. It's okay if it takes a minute, but not 10 minutes to run. Where does that go? Is that high? Is that critical? And second, when things go wrong, we want to find if there's a problem before our customers start calling us. So we want to set up some alerts. But at what point do we alert? How much latency is too much latency for the high priority queue or the low priority queue? And that's where our hero, Sally, comes in with her brilliant idea. We will organize our queues around different allowed latencies with clear guarantees and strict constraints. Now let's unpack that because there's a bunch there. First, we'll define our queues around how much latency a job in those queues might experience. This is the maximum latency we will allow in these queues. And allow may sound a bit naive, but you'll see what I mean in a second. What's important is that you know that if you put a job in those queues, it will start running in no more than this advertised maximum latency. We will name those queues based on that, clearly and unambiguously. Anyone that's looking at a queue needs to know exactly what they can expect from it. Now here's the important part. The name, that's a guarantee. It's a contract. If you put a job in one of these queues, it will start running before that much time elapses. If a queue's latency goes over what it says in the name, alerts go off, fire departments get called, on-call engineers get woken up, and we fix it. That name is a promise, and you can count on it. And that is the key to the whole implementation. So as an engineer, whenever you're writing a job, you choose what queue to put it in based on how much latency you can tolerate. And what that means is, what is the threshold where if the job didn't run by that time, somebody will notice and think that the job is late, or it didn't run, or the system is broken? And that makes it much less ambiguous where to put things. What happens if this job runs an hour later? Will anybody notice? No? Great. You go to the within 1 hour queue. Is 1 hour too much? How about 10 minutes? Can you wait 10 minutes? If that's okay, great. If not, you go to within 1 minute, for example. Now, granted, finding this threshold for these jobs will be easier for some than for others, but you want to try and map out what would happen if you run at different levels of late and figure out what would go wrong. And we need to be realistic, right? There's always a temptation to think everything needs to happen right now, but we need to remember that not everything can happen instantly and be thorough in figuring out how much time we can allow our job to wait and always choose the slowest queue possible. Now, I sense you're probably not very convinced yet, so let's look at why this solves the problem we're seeing in a bit more detail. The key thing here is that the names that we give these queues are clear promises. They're a contract, and they set clear expectations. By putting a job in a given queue, a developer is declaring what the job's needs are. Remember we said earlier one of the problems is that jobs have an implicit amount of time they can wait? That's a requirement those jobs have, which is not documented anywhere and not really actionable. When we set queues up like this, we turn that implicit requirement into an explicit one. If a job is in a within 10 minutes queue, you know it needs to start running in 10 minutes or less, or else. And outside of this is that when you have things like high and low priority queues, you'll be unintentionally mixing up jobs that can tolerate different levels of latency. If your high queue is running, 4 minutes behind, that's probably fine for some jobs, but maybe not for others. And it's not really clear what you can do with that. When you set clear expectations, that's much easier. You already know that all the jobs in the within 10 minutes queue can wait up to 10 minutes. If your queue is running 5 minutes behind, you unequivocally know that's okay because the authors of those jobs explicitly told you that by putting them in that queue. And that's also another one of your problems, right? If our queries are having trouble, and we want to know before our customers find out and fix it as fast as possible. So we want alerts for when things go wrong. If you have people on call, you want them to be paged then if queues breach their latency guarantees. When you have vague names for your queues, how do you set the thresholds for those alerts? How do you know that any threshold that you set is good for every job that's in those queues now or that will be added in the future? With clear queue names, the alert pretty much sets itself. Within 10 minutes, cool, you alert if the latency hits 10 minutes and you're done. And of course, if your alerting is too late, things have already gone wrong. Ideally, we want to try and prevent that from happening, but we also don't want to spend too much money by having too many servers that are idle all the time. These clear promises make it much easier to do auto-scaling and set good thresholds for it. You know precisely what level of latency is acceptable, the queues tell you. You have an idea of how long your servers take to boot up and start helping with the load. You add a bit of margin, and that's your auto-scaling threshold. When you hit that much latency, you start adding servers. At Flex, for example, we use 50% for most of our queues. If you hit 50% of the allowed latency, we start adding servers, one more every few minutes until the latency goes back down below 50%. And 50% was an easy number to choose and a bit arbitrary. We can probably tune that up a little bit for the slower queues, but the truth is it's high enough that most of our queues are running on the minimum number of servers most of the time, and when we get spikes, the queues just deal with it. We almost never get paged for it. Oh, by the way, if you're doing auto-scaling, you always do it based on latency, never the number of jobs in the queue or the CPU, always based on latency. Now, there's a flip side to this. These guarantees don't come for free. Contracts always go both ways. And for us, that means just one simple rule. If you're in a queue that can only tolerate very small amounts of latency, you need to finish running pretty quickly because otherwise you need to run it pretty quickly. That's the flip side to this contract. I call it the swimming pool principle. In a swimming pool, you normally have the fast, medium, and slow lanes, right? And if you want to swim in this lane, you better swim at least this fast, or you need to go to the slower lanes so you don't get it away. In practice, this also applies to our jobs. If you're in a slow queue where jobs can tolerate a good amount of latency, you can run for a while and it's fine. But if you're in a fast queue where jobs need to start quickly, you need to get out of the way pretty fast or you're going to ruin the party for everyone. When you put a job in a given queue, you're signing into that contract. If you break that contract, you'll probably get kicked out of the queue. So we need to set a time limit for each of these jobs that we put in these queues. And what that means is if you want to run, for example, in the within 1 minute queue, you need to finish in these many seconds, or we can't take you in here, sorry. You need to go to a slower queue. Now, to see why that is, there's a bunch of queuing theory formulas to calculate this. That's boring. Just picture this instead. You have here on the left a queue where all of the jobs need to start within 1 minute. And like any other queue, here on the right, we have a number of threads that are working those jobs. And the queue is running its little jobs, and they get out of the way pretty quickly. New jobs arrive, and everybody's happy. Now, imagine what happens if you suddenly start putting jobs in that queue that each take 1 hour from start to finish. What happens to this queue? As soon as one of these threads gets one of those jobs, that thread is now gone for an hour, can't pick up any new jobs. So a very small number of these long-running jobs is going to clog all of the threads in your queue, and no work can get done anymore. If you're going to do auto-scaling, for example, you're going to be adding a new thread for each job that clogs a thread. That's going to be unsustainable. Imagine instead if every job in your queue finishes in 2 seconds, now one single thread can handle a lot of jobs before you breach your promise. You're going to be able to run way more jobs with fewer threads, and it's going to be much easier to keep the latency low. And by the way, this is also why priorities don't work, because you're going to have low priority jobs that run for a long time that clog every single queue in the thread, and then there's nobody left to pick up the high priority ones. So you need to set time limits for each queue. The faster the queue, the faster you need to finish. Now, where you choose to set this depends pretty much on how much money you're willing to spend on servers and on developers. It's a trade-off. If you set the limits too high, if you let the jobs run for a long time, it's going to make your developers' life easier, but you're going to need many more threads, and you're going to spend much more money in servers. If you set them too low, new jobs that need to run with low latency need to be optimized more, maybe refactored, split into different chunks. It's going to be more annoying for your developers, and you're going to spend more time doing that instead of features. You're going to spend more money in developers. It's a balancing act. Now, I like the rule of thumb of setting this target as 1/10 the latency limit. So a job within 1 minute can run for up to 6 seconds, within 10 minutes can run up to a minute, etc. In reality, this is a bit aspirational. You're not going to start here, and it's also going to vary a lot based on the current state of the app and your code base. It's also quite possible that you're going to set this a lot higher at first and spend more money on servers for a while. Now, there are 3 important things that we need to remember, and they're going to be key to this implementation. Number 1, the latency promise in the queue names and these time limits are a contract between the infrastructure and the developers. And like any contract, we need to know if it's broken. If a job is regularly going over these limits, a warning needs to go out to the respective team to either improve it or move it to a slower queue. This isn't a page. It shouldn't wake up anybody in the middle of the night, but it should make it clear that it needs to be fixed. Number 2, there's an implicit social contract here. Remember that inter-team fights that resulted in everybody wanting one queue for each team? This is how you prevent that. If a job is breaching the time limit, there needs to be an explicit permission for people to move it. And of course, we're all going to talk to respective people involved and try to get an idea of what's the best course of action. But if a given job is making queues sad for everyone, you need to have that explicit permission for other teams to move it out, or you will end up back in a situation where every team wants to control their own queues. And finally, respect the principle and focus on latency tolerance. Just because a job finishes quickly and can run in the fast queues doesn't mean that it should. There's going to be generally a temptation to put jobs in the fastest queue that will allow them, basically. Don't do that. You may have jobs that run very quickly, but nobody cares if they're late. Put them in the slower queues. Don't let them get in the way of jobs that are actually sensitive to latency. And this is, in a nutshell, how you can fix the problems that you might be having with your queues. But wait, Daniel, I hear you say, what happened to our merry band of software developers? After her epiphany, Sally proposed this new structure to the team, and they liked it, and they started working on adopting it. Wasn't easy, certainly wasn't quick, but they got there in the end, and there are some useful lessons in how they did it. First, of course, they created the new queues with their alerts, and the rule was that every new job from now on can only go into these new queues. They actually made a custom linter rule to make sure that nobody would forget this. And then they started the huge task of figuring out where all the existing jobs should go, which it's a lot, and it can be a bit daunting. But they found a very clever strategy to do this. First, they started not with the most important things, but with the easiest. For example, some queues can be pretty obvious. They had 2 queues that run overnight maintenance jobs. That's easy, nobody's in a rush for them, just goes into within 1 day. Jobs that took really long to run, for the most part, also got sent to the slower queues. Nobody expected them to run quickly anyway. And then once the easy stuff is moved out, there's not really point in having the queues for every single team anymore. You can just collapse them all back into priorities and save a bunch of money already. And pretty quickly, those 60 queues that they had turned into 9. And this was a massive motivational push. It was so much easier to get the system running with all those fewer queues. And they could see real progress. They were really eager to do the rest. Now, the next trick, that was the best bit. They went on for the jobs that run the most often, the highest volume ones. These are always a candidate for ruining your day, so you want to make sure that they're in the right queue. And these are sometimes hard to categorize, but normally there's not that many of them. And as they kept going down this list, and at one point they realized that they had a lot of different jobs left. There was a lot of work left to do. But the total volume of those jobs was tiny compared to the rest. So here's a little secret. They never actually finished. After a while, the jobs they had left were so few and so quick that there was very little chance they could actually cause problems. So they just merged them all into the default queue and left them there. It wasn't really worth cataloging each one, which left them with this. Now, this was bliss. It was a dream to keep running day to day, but they weren't done. To move faster and keep momentum, they did take a couple of shortcuts. First of all, those speed limits, they set them way higher at first and just threw most servers at the problem. This made it much easier to start putting jobs in the right queues without having to worry too much about their performance. But now they had a clear ordered list of trespassers, jobs that were too slow for the queues, which they would then work on, gradually making them faster, and then gradually lowering these time limits until they got to the sweet spot. They also learned an extremely important lesson: when to break the one rule. You know how I said the latency is the one thing that you care about? That's true, but sometimes there are practical considerations that mean it makes some sense to stray from the path a little bit. For example, some jobs may need some special hardware. Generally, this means a lot more RAM. You can put them in their own queue, And then you can have a few large servers for them instead of making all of the servers for the queue more expensive. Sometimes you have jobs that will want to run one at a time. And that's generally an anti-pattern, but there are some legitimate reasons for that. Having their own queue with one thread and never more than one server lets you do that. And the name makes it clear you should never give that more than one instance. Some jobs do a lot of waiting on I/O. They use almost no CPU. Mailers are like this. You could set really high thread counts for those servers and save money, but that would hurt all the other jobs. Giving them their own queue, again, lets you make the distinctions and save on servers. This is all the usual trade-offs of money versus complexity. And as always, your mileage may vary, but it's sometimes useful to stray from the path a little bit. Just make sure all your queues still have a clear latency guarantee in the name, the usual alerts, and you're golden. And that is how a brave team of developers fixed all of the queuing woes, reached pure operational bliss, and lived speedily ever after. Thank you. Before I go, I do want to leave you with a note. I mentioned some of the most important lessons that our friends learned while implementing this, but there's a lot more and they don't fit in half an hour. You can get a lot more practical advice on how to do this on the repo. There's also all the slides and everything and the recording from this in there. And that's it.
Questions?
You talked about background jobs, but in your experience, can this be applied to online jobs as well? Because fundamentally, this is all queues, right? Even user-driven traffic is pretty much queued in some way on a servers just with a high level of threats.
So if you're thinking about like web requests, for example, right? The problem is how do you distinguish which request can tolerate more or less latency, right? So if you, I'm just going to make something up now, but if you have some sort of router in front of your application that goes, okay, these paths can only take this much latency, these paths can only take this much latency, and you can send them to different pools of servers, you could do that, yeah. That's actually a good idea. Because, yeah, there are some endpoints that you want very snappy responses and some endpoints that don't really care.
More questions? I think that's all. Thank you very much.
Thank you.